And screen share. Okay, good. Cool. So, how's everyone doing?
Not bad.
Pretty good. Good.
All right.
All right. Okay, so starting a 3-lecture series now, proving Katok entropy rigidity, and that will take us up neatly to the instructional break. Hurrah! Okay. Today is a big day because I'm graduating my first PhD student today. Tianyu's exam is at 2 p.m. If anyone wants to come, I've seen the slides and he's going to give a really accessible first hour. It should be pretty cool. So yeah, anyway, just thought I'd advertise that. Having done 2/3 of this course by now, you will understand lots of words. So it should be good if you're available. Okay, I'm just going to remind something. This may be overkill to remind this, but when I do it anyway, we're doing entropy for flows. I'm sure I must have mentioned this before, but you might be wondering, you know, we learned that in discrete time, of course. Maybe flow F equals Ft. So that the measure entropy with respect to a flow is by definition the measure entropy with respect to the time 1 map. And the reason that makes sense is because of the Abramov formula. So Abramov proof for general flows. So you know this is measure preserving flows. That the entropy of the time t map is absolute value of t times the entropy of F1. Okay. So that's one thing to know. I actually don't know where to find that proof apart from the original Abramov. I mean, it's just a short, like 5 or 6 pages. Classic Russian stuff. So yeah, just wanted to remind that, you know, of course, you can do a more intrinsic definition. Well, okay, for the measure version, I mean, you know, there's like, you got to build a partition and, you know, refine the partition in a discrete way. So for the measure entropy, that there really is some kind of discretization that needs to happen just because it's defined in terms of refining these partitions discretely. So, but yeah, but everything adds up great. And of course, on the topological side of the picture, it's the same story. Entropy of the time 1 map equals entropy of the flow. But you can define topological entropy just by going to the n epsilon definitions and writing t epsilon everywhere, and it works out perfectly. So that one's less subtle. So yeah, so the Abramov formula. I mean, also one thing I just wanted to mention about this is we can see here just from this classical formula that, you know, entropy for flows, you know, in great contrast to discrete time, is really dependent on kind of the speed of the flow. It's really dependent on the time parameterization. We can see that here. You know, you take a given flow, you make it run twice as fast, and you know you're going to get twice as much entropy just because of what it's counting. It's counting how many things there are up to time t. You double how fast everything's going, everything gets more complex, or conversely, if you halve how fast everything's going, everything slows down, right? So I think this is an important thing to bear in mind for the current topic. Okay, so let's set a few things up. By the way, Abramov has 2 formulas. This always confuses people. Some people know this formula. Some people know a slightly different formula, which is about induced transformations That's if you take a measure preserving transformation, fix a positive measure set A, and induce on it, it's a formula for how the entropies change. It's the obvious formula one would expect. There's always some confusion between people who know one Abramov formula or the other. He has two formulas. Even more confusingly, they're published in the same edition of the same journal, right next to each other, and both proofs are 6 pages long. So people have a lot of trouble telling these two apart. Anyway, but I've told you, so you know. Okay. So let's get going with notation. MG is a compact Riemannian surface with negative curvature. Okay, so as usual, you know, we're doing surfaces. There's the Gauss-Bonnet theorem. So, you know, we're thinking about things with genus at least 2. So torus with 2 holes or more holes, equipped with a negative curvature metric. Okay, and of course, if genus is greater than or equal to 2, the constant curvature metric will be negative curvature. And of course, there's like a huge amount of variable negative curvature ones too. So notation, okay, so H star G, this is consistent with what we had, is the growth rate of periodic orbits. So periodic orbits are really, really key to this proof. And of course, we proved already H star G equals H top G, the topological entropy. But I'm going to go with the H star G just to emphasize that we're really using the growth rate of periodic orbits version of this in a crucial way. Okay. And okay, we're going to be comparing different geodesic flows. So I need to bring that out in my notation. So FT with a subscript G is going to be the geodesic flow with respect to the metric G. So remember the Riemannian metric, you know, this is an inner product at each tangent space, you know, that's the Riemannian structure. And that structure defines the geodesics. Geodesics are paths of paths that minimize distance. Of course, that depends on what metric you put on there. So you know, the flow is dependent on the metric, and we're building that into our notation because we're going to be comparing different metrics, different geodesic flows. Okay, so mu sub L G is the Liouville measure. For G, and that's as usual on SM. And SM is, as usual, the unit tangent bundle. And in this situation, that means a point in a direction, right? That's all that means. Of course, unit tangent bundle, you know, depends on G. I might need to bring out that dependence at some points. Okay, yes, let's bring that out now. On S superscript GM, unit tangent bundle with respect to G. Okay, so, you know, having unit length in the tangent bundle, that's dependent on the metric, right? It's totally dependent on the metric. So, that space is going to change depending on what metric you're thinking about. Okay. Yeah. Yeah. So the tangent space above each point is, you know, 2-dimensional plane, and then, you know, the unit tangent bundle is going to be, you know, all the unit vectors in that. So it's going to be like a circle, But of course, you know, what is a unit circle will depend on the metric, of course. Okay, just labeling the point, or we're going to be completely lost in a couple of hours of lectures time. Makes sense to be thorough at this point, or we'll have no chance later on. Okay, so, oops, just happened. V, oh. Okay, VG is going to be the total area of M. So, I mean, I'm using B because, you know, I'm thinking volume, but right now we're doing surfaces, so volume is area, right? So just the total mass of the manifold. So that's just a number, right? And finally, M with a G is going to be the normalized Riemannian volume. That's on M. And normalized in the sense of to be a probability measure, okay? So, i.e. M is going, and this normalization is going to matter. So it's just the, it's the measure which is the Riemannian volume, you know, just normalized by the total volume, right? And of course, if at the beginning we just assumed that the thing had area 1, then you know, there would be no difference between mg and vol g. Okay? But it's worth it to keep that extra generality. Okay, so note for a constant negative curvature. Yeah, note for constant negative curvature K. I think we talked about this before. The Liouville entropy. Right, so remember the Liouville measure that this is like the, you know, this is the like natural volume measure on the tangent space, normalized to be probability equals square root of minus k, right, which equals minus 2 pi Euler characteristic over the volume square root. And that's the Euler characteristic. So I think we talked a little before about how to how this can be proved. So I won't go over it again, but remember in the constant curvature case, everything is like totally explicit. There's probably a few ways to see this. Okay, so here's one way. We're doing constant negative curvature. So Liouville measure is measure of maximal entropy. So this number is topological entropy, is volume entropy. So we can compute volumes of big balls, or we just look up a Riemannian geometry textbook and see that they grow at this exponential rate, and that's how we get it. That's how I would get that. But there's other ways to see this too, okay? Anyway, it's a formula, so everything is very explicit, and this equality can surely be looked up using in classical literature. Okay, so that was a lot of prep. Here's a theorem. Katok, I believe this was 82. For any negative curvature metric G on M, the Liouville entropy is less than or equal to minus 2 pi Euler characteristic over VG to the half with equality if and only if constant negative curvature. So. Okay, so this is half of the famous Katok entropy rigidity. You can look at the entropy, the Liouville entropy as like a functional on the space of metrics. So see how your measure entropy changes as the metric varies. What are the properties of this functional? And I don't know how one would guess this intuitively. Well, I'll have a stab at it later. But it turns out that this varies, and it's got a maximum, which can be given, has various interpretations. That this is maybe the most natural because it's kind of in terms of topology. But obviously it's just that number there. Where that's the curvature of the constant curvature metric that goes on here. So this functional can tell you if you're at constant negative curvature. It's maximized at constant negative curvature. So let's say that, i.e., fixing the area, the functional G goes to entropy, to the Liouville entropy, has its maximum at constant negative curvature. Okay, I'm going to prove this one first. The second half of Katok entropy rigidity is that the topological entropy achieves its minimum at constant negative curvature. And then you get a bunch of consequences. In particular, two measures are only the same if their entropies agree. Hang on, I probably just didn't say that right. If two measures have different entropies, then they're definitely different. Among other things, that this shows that the Liouville measure and the measure of maximal entropy can only be the same thing at constant negative curvature, which again is a really nice rigidity result. And the other interpretation is these entropies can tell you this geometric fact you're at constant curvature or not, which is cool. So that's the entropy rigidity. I have a better explanation for why the topological entropy version of this is true. I'll tell you that explanation when we get to it. Let me try and give you some kind of explanation as to why you might kind of imagine that this could possibly be true. Well, one of Katok's slogans, I've heard him say this to me a few times, is that the Liouville measure is dumb. Liouville measure is dumb, right? It just sees what it sees. It's this Riemannian thing. It's not kind of built to really kind of, see the dynamics like the measure of maximum entropy is, right? It's like, it's defined by maximizing how much complexity you see. So it's kind of adapted to the dynamics, whereas the Liouville measure just sees what it sees. And I think the interpretation of this is that a constant negative curvature, of course, everything looks the same all over the space, and nothing is wasted. The Liouville measure sees everything perfectly. The Liouville measure is the measure of maximal entropy, etc. But as soon as you move away from constant negative curvature, the Liouville measure just sees what it sees, and it's dumb, and it kind of misses some complexity. So somehow it just sees what it sees, and it wastes some of the kind of orbit complexity that it could hope to see. So that's some explanation for why it drops off away from the constant negative curvature. Anyone buy that? Okay, I think that's the best intuitive explanation I can come up with, but we're going to see, of course, proof. Any questions before I go on? Okay, so this is what we're proving. Liouville entropy has this maximum with equality only at constant negative curvature. Okay, bit of prep work. Okay, geometry facts, and this will explain why this is a proof for surfaces. Uniformization theorem, everyone knows that, right? I'll state it in the form that is useful for me. Any negative curvature metric G on a surface can be written G equals rho times G0, where rho greater than 0 is a scalar function on M, and G0 is a constant negative curvature metric. Constant is the important word there, with the same area. Okay. So that's the uniformization theorem for Riemannian surfaces. Every surface carries a constant curvature metric, and if you have, if you have a negative curvature metric, that surface must carry a constant negative curvature one, and the two things, and more than that, it carries one which is conformally equivalent. So having this relationship, one metric being a scalar function times another, is called being conformally equivalent. Okay, so there's a conformally equivalent constant negative curvature metric. So I'm sure many of you have studied this kind of thing. Those of you who haven't, you have a choice of looking this up on Wikipedia, or just buying what I'm telling you, or going for a deep dive into why this is all true, and I'll leave that to your judgment, how much to go digging. Okay. Of course, for surfaces, there's not just one constant negative curvature metric, there's a whole bunch of them. These are parameterized by so-called Teichmuller space. And for those of you who haven't heard about this before, the basic idea is, think about the usual torus you draw, like a square torus, right? And we normally say that is the torus. But think about a different lattice, something kind of skewed, some kind of rhombus or something. That is another torus, with the sides identified correctly. Of course, those two tori are identical from the points of view of many types of structure, but from the point of view of conformal structures, angles, shapes of balls, those are the distinct tori. So that square tori and that kind of rhombus type tori are not conformally equivalent. You need a quasi-conformal mapping between them. To map from one to the other, you're going to have a map which sends circles to ovals. Yeah, anywho, and it's like that in negative curvature too. Okay, but in the conformal class, there is a constant negative curvature thing. And you know, this is one of the main reasons this is a surface result. Okay, so comparing metrics. So G1 and G2 are going to be Riemannian metrics. Do a little prep work here. I'm going to define bracket G1 colon G2 to be the following. It's the integral over the unit tangent bundle for G1 of the size of the vector. So that this is a G1 unit vector. Of course, it has a different length with respect to G2. So I'm gonna look at how long this G1 unit vector is with respect to G2, and I'm going to integrate that with respect to the G1 Liouville measure. Okay, and you know, this is some number. I think in Katok he describes this as the average value of G2 length, the G1 length. So when I give that as a slogan, it's certainly some way of measuring one metric in terms of the other. The way this is written, we're not really seeing that denominator there, but it's kind of, you know, it's kind of implicit because, you know, these are linear spaces and this is unit vectors. So yeah, anyway, that's some kind of slogan if you want to understand what this is. Okay, so the heart of this argument is knowing some things about this comparative. Okay, I can't remember. There's a name for this operation now. I can't remember what it is. I'll look it up for next time. Someone gave it a name later. Okay, Katok just introduced it. Yeah, anyway. Lemma 1. Okay. G1 colon rho G1 equals the integral over m square root of rho dm G1. Okay. So obviously this is defined for any pair of metrics, but when one is conformally equivalent to the other, things simplify a lot, right? And note that this is integrating over the unit tangent bundle. This is integrating over the manifold itself, right? So, so recall that the Liouville measure is the normalized volume downstairs locally product are on the circle. So, you know, it's points, you know, it's the space and directions. And on the surface case, so directions is like a circle, right? Okay, so we're going to move from integrating all around these directions to integrating downstairs with this nice simple formula. Okay, so let's check that. Well, there's not that much to check. So proof idea. Note that what is the norm of a vector? You know, it's the square root of g v v, right? So norm of v in the metric rho G1 equals square root of rho at pi of b G1 BB. So also recall oops, just notation. This is just the foot point map. Looks at the point in the direction, just extracts the base point, right? And of course, rho is defined on the manifold. So we're taking a tangent vector and we're just looking at its foot point. Yeah, I mean, that's a definition, right, of this thing. Okay. So yeah, equals square root of the foot point norm v G1. So I won't write any more details. So yeah, let's see how we get this from this. I'm just integrating, I'm just integrating this thing, but this thing is just this. So do it locally. Write this as manifold times a circle, and it just everything decomposes, everything's normalized. So this factor comes out, and I'm just integrating this. Yeah, this just right. I'm integrating the unit tangent bundle. So this term just goes away. I'm going all around the circle, and I'm just left with integrating this downstairs. Okay. You want to fill out those details. I'll leave that as an exercise. Okay, is this clear?
I think so, yeah.
Good. Okay, if G2 equals rho times G1 and G1, G2, the same volume, this operation is symmetric. I think we'll probably use that at some point. And here's the thing which is really gonna drive our proof. This integral, which of course is just equal to this bracket. So the first two things equal this thing on line B, less than or equal to 1 with equality. If and only if rho is identically equal to 1. Okay. So yeah. Right, and of course this thing here is just by lemma 1, that this is equal to G1, G2, right? By lemma 1, and by part A also equals G2, G1, right? Okay. Proof A, so if G2 equals rho G1, then again we can just look up some classical geometry and find out that the volume equals G2 equals rho times the volume of G1. That's in the surface case. I'll just point out that difference. Theorem equals n. we get rho to the n over 2. I'm not doing that case, but I just thought I'd mention that. But in the surface case, you just get this. So dm g2 equals vg1 over vg2 rho dm g1. So, you know, if those numbers are the same, then g1, g2 is the integral over m rho to the half dm g1 equals integral over m rho to the minus 1/2 dm g2, right? Just using that. Equals g2 comma g1, right? Because g1 equals rho to the minus 1/2 g2, right? So, yeah. Okay, nice and easy. All of these tricky proofs have a simple core somewhere. All right, B. Okay, so this is where this whole rigidity thing's coming from. Okay. I mean, everyone knows this, right? I mean, like the vast majority of mathematics, even very fancy mathematics, when you really get to its heart, it tends to be true due to one of a handful of results. Many times it comes down to the triangle inequality when you really boil it down. In this case, it boils down to essentially Cauchy-Schwarz. So yeah, this is really a clever, well, not this level. I mean, the whole Katok entropy rigidity is basically coming from Cauchy-Schwarz. Okay, so B, so integral over m rho dm g1 integral m of 1 dm g2, right? Again, just using this observation here. And just equals 1. And that's because, you know, but by assumption, by the way we set things up, since m is a probability measure. Okay. So by by Cauchy-Schwarz, or you could also, if you wanted to, see this as an application of Jensen's inequality, whichever way you want to think about it. The integral over m of rho to the 1/2 dm g1 all squared is less than or equal to 1 with equality if and only if rho equals 1. Everyone remembers what Cauchy-Schwarz says, right? Should I spell that out a bit more? I can if anyone requests it, but I won't think badly of anyone. I forget classic theorems all the time. I figure if it's easy to find on Wikipedia, why do I need to store it up here, you know? That was bad advice. I take it back, and I'm on camera. Oh, well. I hope my reputation can take it. Okay. All right. All right. Do take a moment to look this up if you don't remember it. And there's no shame in forgetting a big theorem every now and again. It's all about knowing, you know, when you know what you don't know and when it's appropriate to go and look it up quickly. Okay, so yeah, do take a moment to look that up if I just went too fast. You know, this really is the key to the whole whole operation. Good. All right, I'm going to put this in a box because here's the thing that really matters, what we just did. Finding lemma 1 and 2. We have G1 comma G2 equals G2, sorry, colon G1 less than or equal to 1 with equality if and only if the conformal factor rho equals 1. So that's what we just checked. Okay, so what has this got to do with the theorem we are trying to prove? Key result. The word key is something I have a little quirk of overusing when I'm writing grant proposals. The key to this, the key to that, this is key in the theory of blah, but this really is a key result. I'm not overusing it right now. If G2 equals rho G1, both with negative curvature, then I claim that H star G2, growth rate of periodic orbits with respect to the metric G2 is greater than or equal to the Liouville entropy of G1 divided by this comparison thing, G1, G2. Also, the thing on the left is the topological entropy, but I'm just emphasizing that we're using its interpretation as a growth of closed geodesics. Okay, so that's going to take a bit of proving. That probably looks a little mysterious now, but we're going to prove it soon. But let's take that on faith for a moment. Here's the proof of Katok's theorem. Part of it I stated today. Given the key results, so given the key results and the work we've done today, the theorem is easy. Let G0 equal rho G1 with the same volume B and G0 has constant negative curvature. So G0 is this conformally equivalent constant negative curvature thing. Then minus 2 pi Euler characteristic of M over V to the half, as we observed earlier. The topological entropy of G0, this is the constant curvature guy where we know everything that we could possibly want to know. And as we proved in this course, equals growth rate of periodic orbits is greater than or equal to, this is by key result, I'll write that in a moment, H mu L G1 divided by G1 G0. Okay. Okay, and number 2, G0 G1 equals G1 G0 less than or equal to 1, and thus just rearranging what we have above there, H mu L G1 less than or equal to minus 2 pi chi m over v to the 1/2 g1 g0, which is, and of course that last term all comes down to this guy being less than or equal to 1. We've got exactly what we claim. Quality holds only if that conformal thing equals 1, which, as we've seen before, is the same thing as rho equaling 1. Okay. And that is the proof of Katok entropy rigidity, given the main result, and sorry, the key result and the work we've done already today. Any questions?
So we're going to show the key result, right?
We most certainly are. Okay. Yes.
When does the equality hold in the key result? I might have missed that.
When does equality hold in the key result?
Don't we need that as well?
Nope. Nope, doesn't matter. I think, yeah, because we're getting the oh right, sorry. Yes, good point. Yeah, we certainly need equality. You know, when the two things are the same. I think that should be trivial, right? Because G1, G2, yeah, right. So yeah, so let's put a note there, or someone just put a message in. Yes, thanks, Yusuf. Exactly. Yeah, so we get equality for free when rho equals 1. Yeah, thanks. Exactly. I'll write it just as Yusuf said it. Equality is free when rho equals 1, constant curvature. Well said, Yusuf. Thank you. Yeah, and you might wonder if there's a rigidity aspect to that, to this inequality as well. I actually think there might be, but that bit doesn't matter to us because we get the rigidity out of you know, what we know about that term. Yeah. Good. Okay. So at its heart, it's all about getting Cauchy-Schwarz to work for us. But of course, there's some hard work to do. We need that key result. I've only got a couple of minutes left, but I'm gonna start. Proof of key results. I'll pull this over. I'm not going to get very far, but I'll start. T greater than 0 and epsilon greater than 0. Let A epsilon comma T equal the set of B belonging to SG1M, such that, okay, this is going to, yeah, I want to end on this because we're going to see some dynamics now. So some dynamics that we should feel happy with. Okay, so I'm going to look at these integrals, time integrals, minus G1, G2, less than epsilon. Okay. And okay, and this is great because this links up a few things. We know that the measure mu sub L G1 is ergodic. So it was really good we ended up doing it in the order that we did, because that's what we proved last time. We didn't know that until we proved it last time. Okay. So this is just the ergodic theorem. By ergodic theorem, mu sub L G1 A epsilon T goes to 1 as T goes to infinity. Right, because let's just see what we got here. I'm stopping here. Yeah. Cool. What do we got here? G1, G2 is integral over SM B G2 d UL G1. So, use ergodic theorem, on the observable, V goes to norm of V in G2, right? That's a perfectly good observable for using the ergodic theorem. So time averages of these guys go to space average of these guys. So for almost every V, we got the limit of these guys going to this number, the integral, which is just that. Right? So there's a nice bit of conventional ergodic theory in there. So this is a nice thing about this mysterious looking number, is that it can be interpreted as a we can apply the ergodic theorem to understand it in terms of orbits. Okay, cool. So that's where I'll stop there, but obviously we haven't quite seen where this is going to go yet, but at least we started bringing in a bit of dynamics to the proof, and yeah, we'll keep on building this proof next time. I'll stop there. Any questions? And I'm going to post this to Carmen as soon as I finish now. Yeah, I do urge you to read this a little bit, or Friday's lecture will be very mysterious if you can't remember all the notations we set up. So just make sure to look it over immediately before class, or we'll lose track of all the notations.
Sounds good. See you then.
Cool. See you.
See you Friday.
See you.